Part 1. The Accident of Aim. There is something sitting in the sky tonight that should not be visible from where you are standing. Not in any mystical sense. Not in the way that some things feel too large or too strange to be real. In a very literal, very physical sense. The object we are about to spend the next 2 hours with should, by every reasonable expectation, be invisible to any instrument you own, and invisible to every telescope pointed in its direction. It should be a faint, quiet, ordinary-looking core of a distant elliptical galaxy, lost in the background glow of a universe packed with 2 trillion other galaxies, indistinguishable from any of them, a needle in a haystack made of needles. And yet it is not invisible. It is, in fact, one of the most violent and luminous structures in the observable universe. It can outshine every single star in its host galaxy combined, multiplied by factors that begin to make the word bright feel like a category error. And the reason it is visible at all, the reason we can detect it, study it, trace its fluctuations hour by hour across the full sweep of the electromagnetic spectrum, comes down to a single, extraordinary accident of geometry. Its jet is pointed directly at us. That is it. That is the whole secret. The thing we call a blazar is not a special kind of object that evolved differently from its neighbors. It is not built from different materials or powered by a different engine. It is, as best we can determine, the same type of machine that sits at the center of millions of other galaxies across the universe. A supermassive black hole, surrounded by a disk of infalling matter, launching 2 narrow columns of plasma outward along its poles at a significant fraction of the speed of light. The same architecture, the same basic physics. The only difference between a blazar and 1,000 other active galactic nuclei we might casually ignore in a catalog is orientation. The cosmos happened to position this particular object such that one of its jets is aimed directly down our line of sight, pointing at our telescopes, pointing at our detectors, pointing, in the most direct possible way, at us. And that accident of aim transforms everything. A jet that looks unremarkable from the side, a thin, glowing filament extending from a galaxy's core, becomes something unrecognizable when you stare straight into the barrel of it. The radiation that in any other direction would spread out evenly across the sky gets compressed, concentrated, and amplified toward the observer by effects that fall directly out of Einstein's special relativity. Light that would be dim becomes blinding. Variations that would be subtle become dramatic. Energy levels that would be high become, by astronomical standards, almost incomprehensibly extreme. The blazar, in a sense, is the universe's way of showing you what happens when physics runs at full volume and you happen to be standing directly in the path of the speaker. There are somewhere between a few thousand and several tens of thousands of blazars in the observable universe that we have identified so far, though the true number is likely far higher, limited by our detection capabilities rather than the actual population. Each one is a galaxy whose inner engine has, by cosmic coincidence, rotated itself into alignment with a particular observer's perspective. If you could somehow circle around to view that galaxy from a different angle, approaching from above or the side, it would look completely different. You might classify it as a radio galaxy, or a quasar, or a Seyfert galaxy, or one of several other labels that astronomers use to sort the menagerie of active galactic nuclei. The underlying machinery would be the same, the label would change entirely. This is perhaps the most disorienting thing about blazars before you even begin to understand what they are doing physically. The object does not have a single identity. What it appears to be depends entirely on where you are standing when you look at it. We happen to be standing in the wrong place, or the right place, depending on your temperament. There is a useful thought experiment here. Take the Blazar Markarian 421, one of the nearest and best-studied blazars, located about 400 million light-years from Earth. Its jet is pointed at us with a misalignment of probably just a few degrees at most. Now imagine rotating Markarian 421 so that the jet axis swings away, so that instead of being aimed at our galaxy, it is pointed perpendicular to our line of sight, or away from us entirely. What would we see then? We would see a radio galaxy, a moderate luminosity elliptical galaxy with two faint extended radio lobes on either side of the nucleus, jets visible as thin columns of emission if we looked carefully with radio telescopes, and a central brightness that, while still elevated above a normal quiescent galaxy, would not immediately catch the eye or demand extraordinary explanations. The same black hole, the same jet, the same physics, just not pointed at us, not beaming its power directly toward our instruments, quietly doing its thing in a direction where we are not watching. The geometry is everything, and this is not the kind of statement that physicists usually make with comfort. We generally prefer that the physics not depend on the observer's position. But in the case of blazars, the observable properties are so strongly influenced by the geometric relationship between the jet axis and the observer that there is no way around it. The blazar classification is genuinely, irreducibly, an observer-dependent category. An object is a blazar only from certain directions. Now, before we go any further into the deep mechanics of what makes these objects tick, I want to take a moment to establish the scale of what we are dealing with, because the numbers involved in blazar physics have a way of becoming abstracted very quickly, and abstractions lose their weight. So let us be concrete. The black holes at the centers of blazars are supermassive, which in astrophysics means they range from roughly 100 million times the mass of our Sun to, in the most extreme cases, tens of billions of times the mass of our Sun. For context, our own Milky Way's central black hole, Sagittarius A, has a mass of about 4 million solar masses. The black holes powering the most dramatic blazars outweigh that by factors of hundreds to thousands. These are not just large black holes. They are objects whose event horizons, the boundary beyond which nothing, not light itself, can escape, are larger than the distance between our Sun and Neptune. Some of them are larger than entire solar systems, measured from the outermost fringes of their gravitational dominion. And that black hole is not sitting quietly. It is being fed. Gas, dust, stellar debris, and occasionally entire stars that wander too close, are captured by its gravity and spiral inward, forming a vast, hot, magnetized disk that can span hundreds of billions of kilometers. As material in this disk falls inward and accelerates, it heats to temperatures of tens of millions of degrees, radiating across the full electromagnetic spectrum from radio waves to X-rays. This disk alone, for the most active supermassive black holes in the universe, can outshine the combined starlight of every star in a galaxy containing hundreds of billions of suns. And then, separately, additionally, and somehow even more energetically, the black hole launches jets. Not one jet, two, one from each magnetic pole, firing perpendicular to the accretion disk, composed of electrons, positrons, and possibly protons, moving at bulk speeds that in some systems reach 99.5% of the speed of light. These jets can extend for distances that begin to challenge the imagination. Some blazar jets, when you trace them in radio wavelengths, stretch for millions of light-years beyond the host galaxy. The jet of the Blazar 3C31, to pick a well-studied example, extends for roughly 1.6 million light-years on each side of the central engine. That is more than half the distance to the Andromeda galaxy, fired in two opposing directions from a single point. When one of those jets is pointed at you, you see a blazar. When neither is pointed at you, you see something quieter, something classifiable under a different name, something that does not immediately announce itself as among the most powerful sustained emitters of energy in the known universe. We are one of the lucky lines of sight, or unlucky, again depending on your perspective on being aimed at by something that routinely produces gamma rays energetic enough to pass through ordinary matter as though it is not there. In this video, we are going to follow the physics of the blazar from the inside out. We will begin at the black hole itself, trace the mechanism that launches the jet, understand the relativistic effects that transform that jet into the extraordinary beacon we observe, walk through the history of how these objects were discovered and gradually understood, explore the two broad families into which blazars are divided, examine the stunning variability that makes them change brightness dramatically within the span of a single night, and finally arrive at what Blazars have recently revealed about some of the deepest open questions in high-energy astrophysics, questions involving neutrinos, cosmic rays, and the origin of the most energetic particles ever measured arriving at Earth. There is a quality to studying objects like this that I find difficult to articulate precisely, but want to try, because it is part of why this subject matters beyond the raw facts. When you look at a blazar in an image, you see a point of light, maybe a slightly extended smear if the resolution is high enough to start to resolve the jet. Nothing that announces itself as cosmically significant. The sky is full of points of light, and yet the physics crammed into that point, the black hole, the ergosphere, the magnetic fields threading the horizon, the plasma moving at 99.5% of the speed of light, the relativistic beaming amplifying everything by factors of thousands, the neutrinos being fired through the universe at energies that make Earth's best accelerators irrelevant. That physics is happening right now, not in someone's calculation, not in a simulation. Out there, in the physical universe, pointed at us. Every second of every day, continuously, blazars are doing this in the background of the sky, and we are receiving their emissions without any particular fanfare. That quiet running of the universe's most extreme processes in the background, unannounced, is something that I think is genuinely worth sitting with for a moment before diving into the mechanics. Settle in. Get comfortable. This one goes deep. If you are watching this late at night or early in the morning when the world is still quiet, drop a comment and tell me where in the world you are and what time it is. I find it genuinely moving that people watch these videos from every corner of the planet, at every hour of the day and night. And if you are new here, hit subscribe. These videos are built to be long and slow and thorough, and I want to make sure you find them again. Part 2. The Galaxy That Eats. To understand a blazar, you first have to understand that galaxies are not simply passive collections of stars drifting through the universe on quiet orbits. Some galaxies have engines, not metaphorically, not in the way that a particularly dramatic spiral arm might be described poetically as an engine of star formation. Literally, at the center of a growing fraction of the galaxies we observe, and likely at some point in the history of almost every large galaxy, including our own, there exists a structure of extraordinary violence and luminosity, fed by gravity, powered by matter falling into a supermassive black hole, and capable of producing more energy per second than the combined output of all the stars in the galaxy it inhabits. We call these structures active galactic nuclei, usually abbreviated to AGN. And understanding what an AGN is, what it requires, and what distinguishes an active galaxy from a quiet one is the foundation upon which everything else we will talk about tonight rests. Start with the basic picture. At the center of essentially every large galaxy in the observable universe, there is a supermassive black hole. Our Milky Way's central black hole, as mentioned, is about 4 million solar masses. The black hole at the center of the Andromeda Galaxy, our nearest large spiral neighbor, is estimated at somewhere between 100 million and 200 million solar masses. The galaxy M87, an enormous elliptical about 55 million light-years from Earth, harbors a black hole of approximately 6.5 billion solar masses, the one we now have a direct image of, thanks to the Event Horizon Telescope collaboration that released its first image in April 2019 and its polarized light image in March 2021. These black holes are not rarities. They appear to be a standard feature of galaxy formation, growing alongside their host galaxies in a relationship that remains only partially understood. Most of the time, these central black holes are quiet. The black hole at the center of our Milky Way is, by extragalactic standards, essentially dormant. It is not being fed in any significant way. The region around Sagittarius A is relatively empty of the dense, infalling gas that would allow it to accrete substantially. It produces modest emissions, some radio waves, occasional X-ray flares, but nothing that would cause an astronomer in a distant galaxy to classify us as an active galaxy. We are, at this moment in cosmic history, a quiet galaxy with a sleeping engine. But when a supermassive black hole is being fed, when gas, dust, stellar debris, or material from a merging galaxy is falling into it in large quantities, the result is fundamentally different from anything that simply having a black hole would suggest. The process begins with angular momentum, a concept we do not need to belabor at length since its deep mechanics were covered extensively in an earlier video on this channel. The short version is this: gas and material falling toward a black hole almost never falls in a straight line. Almost all infalling matter has some angular momentum relative to the central object, which means it cannot fall directly inward. Instead, it spirals. And as it spirals, conservation of angular momentum causes it to settle into a rotating disk structure around the black hole, a flat, swirling disk of hot plasma called the accretion disk. The accretion disk is not a gentle or serene structure. It is one of the most energetically violent environments in the universe. Material in the inner regions of the disk, where it is closest to the black hole, orbits at significant fractions of the speed of light. The extreme velocity of the orbital material, combined with friction between different layers of the disk moving at different speeds, generates heat. Enormous heat. The innermost regions of an accretion disk around a supermassive black hole in an active galactic nucleus can reach temperatures in the tens of millions of degrees Kelvin, hot enough that the disk radiates primarily in X-rays rather than visible light. It is worth pausing on this temperature comparison for a moment, because tens of millions of degrees is a number that does not translate well into intuitive terms. The surface of the Sun is about 5,778 Kelvin. The core of the Sun, where nuclear fusion occurs, reaches about 15 million Kelvin. The inner regions of an AGN accretion disk can match or exceed the core temperature of the Sun across a region millions of times larger. You are not looking at a single hotspot. You are looking at an extended structure, a disk that in some AGN spans hundreds of astronomical units, that is running at stellar core temperatures across its entire inner portion, and this disk is radiating all of that energy away as electromagnetic emission in real time. As material spirals through the disk and gradually loses angular momentum due to friction and magnetic effects, it migrates inward. When it gets close enough to the black hole, it crosses the innermost stable circular orbit, the closest distance at which matter can orbit without inevitably falling in, and at that point, the material plunges. It falls through the event horizon. It is gone. The energy that powered the disk emission was extracted from the gravitational potential energy of that infalling matter, the energy you would need to lift it back up out of the gravity well to infinity. Here is a number that establishes the scale of this process. The conversion of gravitational potential energy to radiation in an accretion disk around a rapidly spinning black hole can have an efficiency of up to about 42%, meaning that up to 42% of the rest mass energy of the infalling material can be radiated away before it crosses the event horizon. For comparison, nuclear fusion in stars, which we tend to think of as extraordinarily efficient, converts only about 0.7% of the rest mass of hydrogen into energy. An accretion disk around a spinning black hole is, in raw energetic terms, up to 60 times more efficient than the process that powers the Sun. This is the engine at the heart of active galactic nuclei. It is the most efficient large-scale energy extraction process we are aware of in the observable universe. The numbers that this efficiency implies, when combined with typical accretion rates, are staggering. An AGN accreting material at a rate of 1 solar mass per year, a fairly modest rate by the standards of the most luminous quasars, at 10% efficiency, converts the rest mass energy of 1 solar mass worth of material into radiation every 10 years. The rest mass energy of the Sun is approximately 1.8 times 10 to the power of 47 joules. Divided by 10 years, this gives a sustained luminosity of approximately 5.7 times 10 to the power of 38 joules per second. The Sun's actual luminosity is about 3.8 times 10 to the power of 26 joules per second. So even at this modest accretion rate, the AGN outshines the Sun by more than 10 billion times. The most luminous quasars in the universe, accreting at tens of solar masses per year at high efficiency, can outshine a galaxy of hundreds of billions of stars by factors of 1,000 or more. These objects, visible to us from distances of tens of billions of light-years because of their extraordinary intrinsic luminosity, are the beacons that mark the most active phases of supermassive black hole growth across cosmic history. But what makes a galaxy active rather than merely having a large, quiet black hole? The answer is the rate of feeding. A black hole in a quiescent galaxy like our own Milky Way today may be accreting matter at a rate far below what would be needed to produce dramatic AGN activity. The black holes at the centers of the most luminous quasars and blazars in the universe may be accreting at rates of several tens of solar masses per year, swallowing the equivalent of tens of stars the size of our sun every single year. That sustained rate of feeding is what drives the luminosity. The brighter the AGN, the more material is falling in per unit time, the more gravitational energy is being converted to radiation, and the more extreme every associated phenomenon becomes. There is also a structure surrounding the immediate accretion environment that plays an important role in shaping what we observe. Beyond the accretion disk, at distances of roughly a few tenths of a parsec to several parsecs from the black hole, distances that are large in human terms but tiny in galactic terms, there is a region of rapidly moving gas clouds. These clouds are orbiting the black hole at high speeds and absorbing and re-emitting radiation from the inner accretion disk. They produce what are called broad emission lines in the optical spectrum of the AGN, spectral signatures whose width reflects the high orbital velocities of the clouds. Understanding whether these broad line regions are visible to an observer depends critically on the viewing angle, as we will discuss when we get to the unified model. Still further out, at distances from 1 parsec to perhaps 100 parsecs or more, there is a structure that has long been described as a torus, a donut-shaped or ring-shaped region of dusty molecular gas that surrounds the inner AGN structure in a roughly equatorial plane. The torus is opaque. It absorbs the radiation from the inner regions and re-emits it at infrared wavelengths. And critically, it blocks the direct view of the inner disk and broadline region for observers who are looking at the AGN from the side. Observers looking directly down one of the jet axes, which are perpendicular to the disk and torus plane, get an unobstructed view of the inner workings. Observers looking from the side or from the equatorial plane see only the outer, cooler, obscured parts. This geometry is a central pillar of how we understand the diversity of AGN types. Every type of active galactic nucleus, every quasar, every Seyfert galaxy, every radio galaxy, every blazar, is, according to the current standard framework, the same basic structure viewed from a different angle. The engine is the same, the feeding mechanism is the same. What varies is the viewing angle relative to the jet axis and the luminosity of the underlying black hole and accretion system. We will examine this unified model in detail in a later part of this video. For now, the key point is that an AGN is a galaxy whose central black hole is being fed at a significant rate, producing an accretion disk that radiates with extraordinary power across a broad range of wavelengths, and in the case of radio-loud AGN, of which blazars are the most extreme subset, also launching jets of plasma from the polar regions of the black hole. There is one more thing worth establishing here before we move inward to examine the engine more closely. Not all galaxies with active nuclei produce jets. The fraction of AGN that are radio-loud, that is, AGN whose total emission includes a significant contribution from synchrotron radiation produced in relativistic jets, is approximately 10% of the overall AGN population, though this fraction varies with luminosity and redshift and is still being refined by large surveys. Why some black holes produce powerful jets and others in apparently similar environments do not is itself an open question. The black hole spin appears to be part of the answer. More rapidly spinning black holes are better positioned to power jets via the Blandford-Znajek mechanism. The magnetic flux threading the black hole is another part. Systems with more coherent and accumulated magnetic flux produce more powerful jets. The mass accretion rate and the mode of accretion, whether material is falling in efficiently or in a less ordered way, may also play a role. But there is no clean, universal rule that says, given these inputs, you get a jet. The jet launching question is one of the frontier problems in black hole physics, and blazars, as the most extreme and most directly observable jet-dominated systems, are one of the primary tools for attacking it. The galaxy is not simply hosting a black hole, it is actively feeding one. And feeding a supermassive black hole, it turns out, is one of the most dramatic things the universe knows how to do. Part 3. The machine at the center. Let us go closer, much closer. We have established that the accretion disk is hot, energetic, and feeding the black hole. But the accretion disk is not simply a flat, uniform sheet of gas rotating around a drain. It is a layered, magnetized, turbulent, violently convective structure whose internal physics are still, in their fine details, an active area of research. Getting a clear mental picture of what this disk actually looks like, or would look like, if you could somehow position yourself nearby and survive it, which you could not, is worth the effort, because everything downstream of the disk, including the jet, including the blazar we are working toward, depends critically on what the disk does. The disk is brightest and hottest in its innermost region. For a supermassive black hole of 1 billion solar masses or more, the innermost stable circular orbit is at a distance that in absolute terms sounds large, tens of millions of kilometers, but relative to the overall scale of the system, it is exceedingly close. The temperature of the disk at these innermost regions scales inversely with the black hole mass in a way that means the highest temperatures are actually found in stellar mass black holes rather than supermassive ones. For a supermassive black hole, the peak disk temperature tends to fall in the ultraviolet portion of the spectrum, meaning the disk's thermal emission peaks at ultraviolet wavelengths before being reprocessed and scattered into other wavelength ranges by surrounding material. Moving outward from that inner edge, the disk temperature decreases. The outer disk is cooler, perhaps thousands rather than millions of degrees, and emits primarily in the optical and infrared. The overall spectrum of the disk is therefore a superposition of blackbody radiation, from different radii at different temperatures, producing what is called a multi-temperature blackbody spectrum that stretches from the infrared through the optical and into the ultraviolet and soft X-rays. The disk is also not perfectly smooth. It is threaded by magnetic fields that arise from the initial magnetic field, carried in by infalling material, and then amplified by the differential rotation of the disk itself. Inner parts of the disk rotate faster than outer parts, the classic behavior of a non-rigid rotating system in a gravitational field, the same behavior that governs the motion of planets in the solar system or the moons of a planet. This differential rotation stretches and wraps any initial poloidal magnetic field into a predominantly toroidal one, and the interaction between the rotation and the magnetic field drives the magnetorotational instability, a specific type of turbulence that is critical for understanding how angular momentum actually moves outward through the disk. This is one of the less intuitively obvious aspects of accretion physics. For material in the disk to spiral inward and eventually fall into the black hole, it must lose angular momentum. Angular momentum, as we know from the earlier discussion, is conserved. It cannot disappear. So for matter to fall inward, angular momentum must be transferred outward, carried by something from the inner disk to the outer disk, and eventually away from the system entirely. For a long time, ordinary viscosity from random thermal motion was thought to be responsible, but calculations showed that ordinary viscosity is far too weak by many orders of magnitude to explain the observed accretion rates in AGN. The magnetorotational instability, which was described in its modern astrophysical form by Stephen Balbus and John Hawley in 1991, resolves this problem. The instability creates turbulence in the magnetized disk, on a scale that provides the effective viscosity needed to drive angular momentum outward and material inward at the rates we actually measure. To visualize the magnetorotational instability, think about two fluid elements in the disk connected by a magnetic field line. If the inner element moves slightly inward, it loses angular momentum and begins to orbit slightly faster. The outer element, connected by the magnetic tension of the field line, is dragged forward, gaining angular momentum. But gaining angular momentum causes the outer element to move to a larger orbit, and losing angular momentum causes the inner element to fall to a smaller orbit. They diverge. The field line stretches. The tension increases. The result is a feedback instability that drives turbulence throughout the disk, converting the ordered differential rotation into disordered turbulent motion, and that turbulence provides the effective viscosity that drives accretion. It is one of those results in theoretical astrophysics that feels inevitable in retrospect, and yet took decades to be worked out properly. Above and below the disk, there is a structure called the corona, a hot, diffuse, magnetized region of electrons that has been heated to extremely high temperatures, on the order of 1 billion degrees or more, by mechanisms that are not fully understood, but appear to involve magnetic reconnection events similar to the solar corona on our own sun, but vastly more energetic. This coronal region plays an important role in the X-ray emission of AGN. The extremely hot electrons in the corona upscatter thermal photons from the disk via the inverse Compton process, boosting those photons to X-ray energies. The corona of an AGN accretion disk is a constant source of hard X-rays, observable by space-based X-ray telescopes. Beyond the disk and corona, at distances of roughly tenths of parsecs from the central engine, the broadline region, those rapidly moving gas clouds mentioned earlier, orbits in the intense radiation field of the inner AGN. These clouds are photoionized by the ultraviolet and X-ray radiation from the inner accretion system, meaning the intense radiation field is knocking electrons off atoms in the clouds, and then those electrons are recombining, emitting photons at specific wavelengths as they do. Because the clouds are orbiting at high speeds, velocities of thousands of kilometers per second, the emission lines they produce are Doppler broadened across a wide range of wavelengths, giving rise to the broad emission lines that are one of the defining spectral features of Type 1 AGN and flat-spectrum radio quasars. All of this, the disk, the corona, the broadline region, is enclosed in a system whose total spatial extent, from inner edge to outer edge of the broadline region, might be a fraction of a parsec. That is roughly 3 light-years or less from edge to center. The entire engine that can outshine a galaxy of hundreds of billions of stars fits comfortably within a region smaller than the distance from our sun to the nearest star. This is where the Blazar's power originates. This is the furnace. But the furnace is not the end of the story, not even close. Because something in this region, something that physicists have understood in broad outline for decades and are still working to understand in precise detail, is launching the jet. And the jet is where blazars really become blazars. The jet launch mechanism is, in its most widely accepted theoretical form, a process that was first described mathematically by Roger Blanford and Roman Znajek in 1977. It is called the Blanford-Znajek process, and it is one of the more remarkable intersections between general relativity and astrophysics that our era of physics has produced. To understand it, you need to know one thing about rotating black holes that has no equivalent in ordinary human experience. A rotating black hole does not simply sit in space and curve it, it drags it. The space-time around a rotating black hole, a Kerr black hole, named after the mathematician Roy Kerr who found the exact solution to Einstein's field equations for this case in 1963, is being continuously swept around in the direction of the black hole's rotation. This is called frame dragging, or the lens-Thirring effect, and it means that nothing, not even light, can maintain a fixed orientation relative to distant space as it orbits close to a rapidly spinning black hole. The fabric of space-time itself is being pulled into rotation by the spin of the mass at its center. The region in which this effect is strong enough to force even light to rotate in the direction of the black hole's spin, even against all other considerations, is called the ergosphere. The ergosphere extends outside the event horizon, meaning that objects can enter the ergosphere, be affected by this rotational drag, and still escape back to infinity if they have enough energy. But the ergosphere is also a region in which it is impossible for anything to remain stationary relative to the distant universe. Everything inside it is compelled to rotate with the black hole, whether it wants to or not. This region, the ergosphere, is the engine compartment of the Blanford-Znajek process. Here is how it works in broad strokes. Magnetic fields from the accretion disk thread the ergosphere and the event horizon itself. The frame-dragging effect twists these magnetic field lines, winding them into a helical configuration. This winding creates a pointing flux, a propagating electromagnetic energy flux, directed outward along the rotation axis of the black hole. The black hole's rotational energy is being converted, through the intermediary of the magnetic field, into an outward-directed electromagnetic flow. That flow is what inflates and powers the jet. The efficiency of this process scales with the square of the black hole's spin parameter, a number between 0 and 1 that describes how close to maximally rotating the black hole is. A black hole spinning at close to its maximum theoretical rate extracts energy far more efficiently than a slowly rotating one, and the magnetic field strength threading the horizon matters enormously. The more coherent and strong the large-scale magnetic field, the more effective the Blandford-Znajek mechanism becomes. Some of the most powerful jets in the universe appear to be powered by black holes that have accumulated not just mass, but also an enormous amount of ordered magnetic flux, a scenario called the magnetically arrested disk state, in which the magnetic field has become strong enough to alter the structure of the inner accretion flow itself. The Blandford-Znajek process is not the only proposed mechanism for jet formation, and there is a related process called the Blandford-Payne mechanism that extracts energy and angular momentum from the accretion disk itself rather than directly from the black hole spin. In the Blandford-Payne picture, magnetic field lines threading the disk at large angles to the disk surface act as channels through which material can be flung outward by the combined effects of rotation and magnetic tension, like balls rolling down a spiral ramp anchored to the rotating disk. The material gains angular momentum from the rotating disk, climbs the magnetic field lines, and is flung outward in a centrifugally driven wind that carries mass and angular momentum away from the disk. When the magnetic field is organized on large scales, and the geometry is right, this disk wind can be collimated into a jet. In real AGN systems, both the Blandford-Znajek extraction of black hole spin energy and the Blandford-Payne disk wind likely operate simultaneously, with their relative contributions depending on the details of the magnetic field geometry and the spin of the black hole. What both mechanisms share is the central role of large-scale, organized magnetic fields. Without these fields, the extraordinary collimation and power of AGN jets cannot be achieved. The disk is a turbulent, tangled environment. The magnetorotational instability is generating disordered turbulence throughout the disk body, and it is not obvious that organized large-scale fields can persist against that disorder. Yet observations of AGN jets tell us they must. The jets are highly collimated, narrower than any simple gas dynamic model would predict, and their polarization properties reveal that the magnetic field has a strong helical component, at least in the parsec-scale radio jet structures accessible to very long baseline interferometry. The organization of the magnetic field in the jet is itself a major unsolved problem in jet physics, and it connects to the question of what maintains the jet's integrity as it propagates from sub-parsec scales near the black hole out to megaparsec scales in the extended radio lobes. The machine at the center is an accreting, rapidly spinning black hole, extracting its own rotational energy through magnetic fields and firing it outward at relativistic speeds. What those speeds do to the light and radiation coming from that jet is where the story of the Blazar truly begins. Part 4. The Jet and the Impossible Speed. The jet has left the engine. Whatever the precise mixture of processes launched it, the Blandford-Znajek extraction of black hole spin energy, the Blandford-Payne torque from the disk, the complex magnetic self-organization of the plasma in the funnel region above the black hole's poles, it is now moving outward. It is a narrow, highly collimated stream of plasma, electrons, positrons, and likely some protons, threaded with a helical magnetic field, moving at bulk velocities that in some systems reach 99.5% or more of the speed of light. And here, right here, is where something genuinely remarkable enters the physics. Not remarkable in the sense of being exotic or unfamiliar to physicists. The effects we are about to describe are standard special relativity, things that have been experimentally confirmed in particle accelerators and in astrophysical observations for decades. Remarkable in the sense that their intuitive consequences are deeply counterintuitive, and that understanding them is necessary for understanding why a blazar looks the way it looks, varies the way it varies, and is as bright as it is. The effect is called relativistic beaming, and it is a consequence of how light and radiation behave when they are emitted by a source that is moving toward the observer at close to the speed of light. Start from a simpler case. Imagine a train horn. You already know this. A train approaching you sounds higher in pitch than a stationary train, and a train moving away from you sounds lower. The source emitting sound waves that are moving toward you causes successive wavefronts to pile up, shortening the wavelength and raising the frequency. This is the Doppler effect, and it applies to light exactly as it applies to sound, with appropriate relativistic corrections at high speeds. Now take this further. Imagine not just a sound source, but a light source, a lamp mounted on the front of our hypothetical train. At ordinary train speeds, the Doppler effect on the frequency of the light would be so small as to be essentially unmeasurable. But now imagine the train moving at 99% of the speed of light. The Doppler effect is now enormous. The light being emitted forward in the direction of motion is shifted dramatically to higher frequencies, from visible light into ultraviolet, into X-rays, potentially into gamma rays. The energy of each photon is boosted by a large factor, and crucially, in the relativistic case, the light is not just frequency shifted, it is also beamed. What beaming means is this: a source emitting radiation isotropically, equally in all directions, in its own rest frame, when moving at relativistic speeds toward an observer, does not appear to emit equally in all directions from the observer's perspective. The radiation is concentrated, focused, compressed into a cone pointing toward the direction of motion. An object moving at 99% of the speed of light effectively beams something like half of its total radiation into a cone of about 8 degrees around the forward direction. An object moving at 99.5% of the speed of light concentrates its emission into an even narrower cone. The mathematics of this involves the Lorentz factor, written with the Greek letter gamma, which at 99.5% of the speed of light has a value of roughly 10.5. The general result is that the Doppler factor, the combined effect of the Doppler shift in frequency and the aberration of radiation, can amplify the observed flux from a relativistic source by factors of the Doppler factor raised to the third or fourth power, depending on the specific geometry and spectrum of the emission. For Lorentz factors in the range of 10 to 30, which are not unusual for blazar jets, this means the intrinsic luminosity of the jet is amplified by factors of thousands to hundreds of thousands in the direction it is pointing. This is why blazars appear so bright. Not because they are intrinsically more powerful than other AGN with jets pointing in different directions, though the most powerful ones are genuinely extreme, but because the relativistic beaming effect creates an enormous apparent enhancement of the brightness for observers who happen to be in line with the jet. The jet emits a certain amount of energy in its own rest frame, but to the observer looking directly into it, that energy appears vastly magnified. There is a second relativistic effect specific to jets moving very nearly toward the observer that has a beautiful and initially deeply confusing observational signature. It is called apparent superluminal motion. When radio astronomers began making high-resolution observations of the jets in active galactic nuclei using very long baseline interferometry, a technique that effectively combines radio telescopes separated by distances of thousands of kilometers to achieve angular resolutions far beyond what any single telescope could provide, they found something that appeared to violate a fundamental law of physics. Features in the jets, bright spots, knots, regions of enhanced emission, appeared to be moving across the sky at speeds greater than the speed of light. Not by a small margin. Some features appeared to be moving at 10, 15, even 20 or more times the speed of light. This is, of course, impossible. Special relativity guarantees that no material object or signal can travel through space faster than light. And the jet material is not actually moving faster than light. What is happening is a projection illusion caused by the combination of two facts: The jet is moving at near light speed, and the light emitted from different positions along the jet takes different amounts of time to reach the observer. Here is the intuition. Imagine a component of the jet moving at 99% of the speed of light at a small angle to the line of sight. When the component emits a photon near the start of an observed interval, that photon begins traveling toward you. Then the jet component moves forward, nearly as fast as the first photon, covering a large distance in a short time. When it emits a second photon, that photon is much closer to you than the first one was when it was emitted, so it has much less distance to travel. The result is that the two photons arrive at your telescope in very close succession, far closer together in time than the actual elapsed time between the emission events. The component appears to have traveled a large distance in a very short time. The apparent velocity, calculated naively as distance divided by time, can greatly exceed the speed of light, even though nothing is actually moving faster than light. The apparent superluminal motion is a geometric illusion created by the finite travel time of light from a source moving nearly as fast as light itself. There is a second relativistic effect, specific to jets moving very nearly toward the observer, that has a beautiful and initially deeply confusing observational signature. It is called apparent superluminal motion. When radio astronomers began making high-resolution observations of the jets in active galactic nuclei using very long baseline interferometry, a technique that effectively combines radio telescopes separated by distances of thousands of kilometers to achieve angular resolutions far beyond what any single telescope could provide, they found something that appeared to violate a fundamental law of physics. Features in the jets, bright spots, knots, regions of enhanced emission, appeared to be moving across the sky at speeds greater than the speed of light. Not by a small margin. Some features appeared to be moving at 10, 15, even 20 or more times the speed of light. This is, of course, impossible. Special relativity guarantees that no material object or signal can travel through space faster than light, and the jet material is not actually moving faster than light. What is happening is a projection illusion caused by the combination of two facts. The jet is moving at near light speed, and the light emitted from different positions along the jet takes different amounts of time to reach the observer. Here is the intuition. Imagine a component of the jet moving at 99% of the speed of light at a small angle to the line of sight. When the component emits a photon near the start of an observed interval, that photon begins traveling toward you. Then the jet component moves forward, nearly as fast as the first photon, covering a large distance in a short time. When it emits a second photon, that photon is much closer to you than the first one was when it was emitted, so it has much less distance to travel. The result is that the two photons arrive at your telescope in very close succession, far closer together in time than the actual elapsed time between the emission events. The component appears to have traveled a large distance in a very short time. The apparent velocity, calculated naively as distance divided by time, can greatly exceed the speed of light, even though nothing is actually moving faster than light. The apparent superluminal motion is a geometric illusion created by the finite travel time of light from a source moving nearly as fast as light itself. Apparent superluminal motions of 10 to 20 times the speed of light have been measured in multiple blazars, and this observation is entirely consistent with the relativistic beaming framework. In fact, the combination of very high apparent superluminal velocities with very high variability and very high brightness temperature, the apparent temperature you would need for a thermal source to produce the observed radio flux, forms a mutually consistent picture that essentially requires Blazar jets to be moving at bulk Lorentz factors of at least several, and often tens of times the minimum energy configuration. The Mojave program, monitoring of jets in active galactic nuclei with Vilba experiments, has been conducting systematic long-term monitoring of blazars and other AGN jets at radio wavelengths using the Very Long Baseline Array for more than 2 decades. It has measured apparent superluminal motions in dozens of blazars, finding that the highest Lorentz factors are associated with the most luminous and energetic sources, and that the distribution of apparent velocities among blazars is consistent with apparent population of jets spanning a wide range of intrinsic velocities with Lorentz factors, from a few up to about 40 in the most extreme cases. These measurements represent the most direct observational constraint we have on the bulk Lorentz factors of Blazar jets, and they tell us that the plasma in these jets is genuinely moving at speeds within fractions of a percent of the speed of light. The jet is a relativistic fire hose, and we are standing directly in front of it. The beaming amplifies everything. The variability, which is intrinsic to the jet emission physics, is further compressed in time because of the light travel time effects we just discussed. What takes days in the jet's rest frame may appear to take only hours from our perspective. The spectrum, which spans from radio through gamma rays in the jet's own emission frame, gets shifted and amplified so that the highest energy end of it reaches energies that in some blazars touch the territory of gamma rays with individual photon energies hundreds of billions of times the energy of visible light photons. There is also a subtler consequence of the beaming that is worth pausing on, because it matters for how we interpret the blazar population. Because the beaming amplifies emission only toward the observer, and because jets are fired in two directions simultaneously, only one jet, the approaching one, is typically visible as a bright blazar. The receding jet, moving away from the observer at near light speed, is Doppler dimmed rather than boosted, and becomes effectively invisible at most frequencies. If you are cataloging blazars, you are therefore sampling only a small fraction of all the AGN with jets. For every blazar you can see pointing at you, there are estimated to be on the order of 2 gamma squared to 2 gamma cubed objects, roughly hundreds to a few thousand, for typical Lorentz factors, whose jets are oriented in other directions and which you observe as radio galaxies, quasars at wider angles, or Seyfert galaxies depending on their luminosity and orientation. The blazar population, large as it is, represents just the tip of the iceberg of all AGN that are actively launching jets. We happen to see only those that are pointing at us. The jet is pointed at us, the beam is on, and the result, built up from a black hole's spin, threaded through magnetic fields in an ergosphere, fired at relativistic speeds, and observed through the lens of special relativity's most dramatic effects, is one of the most extreme persistent sources of energy in the observable universe. It is time to trace how we found out it was even there. Part 5. The History of an Accidental Discovery. In 1929, a German astronomer named Kuno Hofmeister published a catalog. The catalog contained 354 objects that Hofmeister had observed and classified as variable stars. Stars within the Milky Way galaxy whose brightness fluctuated over time in ways that were unusual, irregular, or not yet understood. Hofmeister was a systematic and careful observer, working from the Sonneberg Observatory in what is now the state of Thuringia in Germany, and his catalog was a serious piece of scientific work that contributed genuinely to the growing understanding of stellar variability at the time. One of the objects in his catalog was listed under the designation BL Lacertae, meaning it was located in the direction of the constellation Lacerta, the lizard. It got the letters BL because of the convention for naming variable stars, which assigns Greek letters and then Roman letters to variable stars within a given constellation as they are discovered. BL was simply its place in a long queue of stars that varied in ways that made them interesting enough to catalog and study further. Hofmeister noted that BL Lacertae varied irregularly in brightness, not in the regular periodic way that pulsating stars or eclipsing binary stars vary, but erratically, unpredictably, in a way that did not fit any standard model of stellar variability he was familiar with. It was an oddball, worth watching, but not yet alarming. It sat in his catalog as one of many unresolved puzzles in a sky full of them, and there it remained for nearly 4 decades while astronomy continued to advance around it. In 1968, an astronomer named John Schmidt, working at the David Dunlap Observatory in Ontario, Canada, was conducting a survey of radio sources and matching them to optical counterparts. He found that BL Lacertae, the supposed irregular variable star, coincided precisely with the position of a bright radio source. This was unusual. Variable stars within the Milky Way do not typically emit strongly in the radio spectrum. Something was wrong with the classification. Further investigation revealed something more disturbing. BL Lacertae did not have the spectrum of a star. It did not have clear absorption lines at the expected wavelengths for any stellar type. What it had was a nearly featureless optical spectrum, a smooth, continuous glow, with none of the sharp spectral fingerprints that astronomers depend upon to measure distances, temperatures, and compositions of objects in the universe. This featurelessness was not just strange, it was, in the language of a spectroscopist, essentially information-free. The spectrum was telling them almost nothing about what the object was. The decisive blow to the variable star hypothesis came when astronomers measured the object's faint surrounding glow, the extremely dim background of light that could be detected around the bright central source. The redshift of this surrounding light, which proved to be the light of a host galaxy underlying the central point source, measured at approximately z equals 0.07. For readers unfamiliar with the language of cosmological redshifts, a redshift of 0.07 corresponds to a recessional velocity of about 21,000 kilometers per second relative to the Milky Way, placing the object at a distance of roughly 900 million light-years. 900 million light-years away. An irregular variable star sitting 900 million light-years from Earth is not a variable star. It is not within the Milky Way. It is not even close to the Milky Way. It is, by any reasonable measure, a galaxy, or more precisely, the extraordinarily bright core of a galaxy, burning so intensely in its central regions that it outshines the entirety of its host galaxy, and appears, to a telescope without sufficient resolution to see the surrounding fuzz of starlight, as nothing more than a bright, varying point. BL Lacertae had been misidentified for nearly 40 years. What astronomers had been casually tracking as a peculiar but not particularly alarming Milky Way variable star was, in fact, a supermassive black hole 900 million light-years away, launching a plasma jet at close to the speed of light, with that jet aimed almost directly at Earth and amplified by relativistic beaming to a degree that made it visible to modest optical telescopes despite its absurd distance. The cascade of realizations that followed this discovery deserves careful attention, because each step in the process of identifying BL Lacertae for what it truly was represents a genuine historical moment in the development of extragalactic astronomy. When Schmidt matched BL Lac to a radio source in 1968, the natural question was whether this variability at radio wavelengths was telling astronomers something important. Radio emission from a source within the galaxy is common. Pulsars, supernova remnants, regions of ionized gas around massive stars, and various other structures all emit radio waves. But BL Lacertae was varying at radio wavelengths in a way that was not typical of any known galactic source. It was bright and variable and spectrally flat. Its radio emission did not fall off steeply at higher frequencies the way most radio sources do. This flat radio spectrum was a clue, but a clue not yet interpreted. The spectroscopic observations that followed were even more puzzling. When astronomers pointed spectrographs at BL Lac and tried to read the story of the light it was emitting, trying to identify the spectral lines that would fingerprint its composition and let them calculate its distance through the Doppler shift, they found nothing. The spectrum was almost entirely featureless. In a universe full of objects whose spectra shout their identities through emission and absorption lines, BL Lac was apparently silent. This silence was, paradoxically, the most informative thing about it. It meant that whatever was producing the optical emission was non-thermal, continuous, and so bright that it overwhelmed any thermal or line emission from underlying structures. And non-thermal, continuous, beamed optical emission, on that scale, was the signature of exactly the kind of relativistic jet that was already being discussed in the context of quasars and radio galaxies. When the faint host galaxy was finally detected beneath the bright central source, and when its redshift could be measured, the distance was confirmed, and from that distance the intrinsic luminosity of the central source could be calculated. What you find, when you work through the numbers for BL Lacertae during one of its typical bright states, is a luminosity in the range of 10 to the power of 45 to 10 to the power of 46 ergs per second, the equivalent of trillions of suns radiating simultaneously. That luminosity, from a region within the jet that light travel time arguments constrain to be smaller than the solar system, is not the product of a star or any collection of stars. It is the product of a relativistic jet pointed at you, boosted by Doppler beaming, by factors of hundreds to thousands above the intrinsic jet emission. This discovery, and the subsequent recognition that B.L. Lacerté was not alone, that there was a whole population of objects with similar characteristics scattered across the sky, created the new category of B.L. Lacerté objects, or BL-LAC objects. These were AGN with featureless optical spectra and rapid, high-amplitude variability, understood to result from the relativistic beaming of jet emission that was so powerful it overwhelmed the thermal emission from the accretion disk and the spectral emission lines from the broadline region and host galaxy, leaving behind only the non-thermal, broadly continuous spectrum of the jet itself. But BL-LAC objects were not the only type of beamed AGN that astronomers were encountering. A second class existed that shared many of the variability and radio properties of BL-LAC objects, but which had prominent broad emission lines in their optical spectra. Lines that appeared when the jet was not quite bright enough to completely swamp the thermal emission from the inner accretion system. These were called flat-spectrum radio quasars, abbreviated FSRQs, and they appeared to be related to but distinct from BL-LAC objects in ways that were not initially clear. The word Blazar, combining BL-LAC with quasar, was coined in 1978 at a conference at the University of Pittsburgh, and became the standard term for both BL-LACs and FSRQs as a unified category of jet-dominated AGN observed along the jet axis. The terminology has stuck, and today astronomers use Blazar to mean any AGN in which the jet is pointing close to the line of sight and the observed emission is dominated by the beamed radiation from that jet. B.L. Lacerté itself, as the prototype of the BL-LAC subclass, has been one of the most intensively observed blazars in the sky ever since. It fluctuates in apparent brightness between roughly magnitude 14 and magnitude 17 on timescales that range from minutes to months, a range of about a factor of 15 in brightness, just from the brightest to the faintest observed states. In January 2021, it experienced a remarkable flaring event, reaching a magnitude of approximately 11.45 in the R-filter band, bright enough to be detectable with a reasonably equipped backyard telescope. That level of brightness, coming from a source 900 million light-years away, gives some sense of the energetics involved. And in 2025, as noted earlier in this video, B.L. Lacerté surprised astronomers again. A Polish-German collaboration studying the object found it switching between X-ray spectral behaviors characteristic of completely different Blazar subclasses, on timescales short enough to rule out gradual evolution, and with a record-breaking X-ray flux that exceeded any previous measurement from this source. The object that gave its name to an entire class was found to be escaping the boundaries of that class, behaving in ways that current theoretical frameworks cannot cleanly accommodate. The prototype had become a puzzle, which is, if you think about it, exactly the kind of thing a pioneer Blazar might be expected to do. The history of Blazar discovery is, in a sense, a history of the universe surprising astronomers by being much more violent and energetic in certain specific directions than in others. The objects were always there. The physics was always operating. What took time was recognizing that a faint, erratic, featureless point of light in the constellation of the Lizard was not what it appeared to be, and that understanding why it was not what it appeared to be would eventually open a window into some of the most extreme physics in the observable universe. Part 6. The Two Faces of the Blazar. Not all blazars are the same. This might seem like an obvious statement. Of course, objects in the same broad category vary among themselves. But in the case of blazars, the differences between the two main subclasses are interesting not just as classification details, but as clues to what is physically different between two different modes of operation for the central engine. The division between B.L. Lacerté objects and flat-spectrum radio quasars is not arbitrary. It reflects real differences in the accretion rate, the structure of the immediate environment around the black hole, the power of the jet, and ultimately, the kind of radiation the jet produces at different energies. Let us start with the most immediately obvious difference, the optical spectrum. BL-lac objects, as mentioned, have featureless or nearly featureless optical spectra. When you spread out the light from a BL-lac object using a spectrograph, you see a smooth, continuous, featureless continuum of light. No sharp emission lines, no absorption lines, or at most extremely weak ones. This featurelessness is a direct consequence of the jet emission being so strong that it swamps the spectral signatures that would otherwise come from the thermal accretion disk and from the gas clouds in the broadline region. The jet is so bright compared to everything else that it dominates completely, burying all spectral features under its non-thermal continuous glow. Flat-spectrum radio quasars, on the other hand, do show prominent broad emission lines. Their spectra are clearly those of active galactic nuclei, strong, broad features from hydrogen, carbon, and other elements in the rapidly orbiting gas clouds of the broadline region. The jet in an F-circ is still very bright and very beamed, but it is not quite powerful enough relative to the thermal emission from the disk and the broadline region to completely overwhelm those signatures. They remain visible, distinguishing these objects from BL-lacs. The current understanding holds that this spectral difference maps onto a genuine difference in the rate at which material is falling into the black hole. FSRQs are the high accretion rate blazars. Their black holes are being fed at a faster rate. Their accretion disks are brighter and more luminous. Their broadline regions have more gas in them and are more strongly illuminated. And their jets, while powerful, are not so dominant over the disk emission that all spectral features are erased. BL-lac objects tend to have lower accretion rates. Their black holes are being fed more slowly. The disk is less luminous relative to the jet. The broadline region is either weaker or essentially absent, and the featureless jet emission dominates almost entirely. There is a further subdivision that is important and that adds another dimension to understanding blazar diversity. Blazars can also be categorized by the peak frequency of their synchrotron emission, the radiation produced when relativistic electrons in the jet spiral around the magnetic field lines of the jet and emit radiation. The frequency at which this synchrotron emission peaks varies dramatically between different blazars, and this variation tracks something real about the energetics of the electron population in the jet. Low-frequency peaked blazars, sometimes called low synchrotron peaked or LSP sources, have their synchrotron emission peak in the infrared or optical. Their electrons, on average, are relativistic, but not extremely so. High-frequency peaked blazars, sometimes called HSP sources, have their synchrotron emission peak in the X-ray band. Their electrons have been accelerated to much higher energies. In the most extreme cases, sources with names like Markarian 501 and 1ES 0229 plus 200, the synchrotron peak can be pushed into the X-ray band at tens of kiloelectron volts or beyond. The pattern that emerges when you look at these properties together is striking. FSRQs tend to be powerful, high-luminosity systems at high accretion rates with low synchrotron peaked emission. BL-lac objects tend to be less powerful, lower accretion rate systems that span a range from low to high synchrotron peaks. This progression, called the Blazar sequence, was first formalized in the late 1990s by a team of researchers, including Gabriele Ghisellini, Paolo Padovani, and collaborators, examining the distributions of blazar properties as a function of luminosity. The core observation that motivated it was that higher power blazars tend to have their spectral energy distributions peak at lower frequencies. Both the synchrotron peak and the inverse Compton peak shift toward lower energies as luminosity increases. Lower power blazars tend to peak at higher frequencies. The physical interpretation is this: in high luminosity, high accretion rate systems, the jet carries more photons from the accretion disk and broadline region that can serve as seed photons for inverse Compton scattering. More seed photons means more rapid cooling of the electron population. The electrons lose energy faster because they are encountering more photons to upscatter. This faster cooling reduces the peak energy of the electron distribution, which shifts the synchrotron peak to lower frequencies. In lower luminosity systems with sparser photon environments, the electrons cool more slowly, can maintain higher energies, and produce synchrotron emission peaking at higher frequencies. The Blazar sequence is therefore not just a classification scheme. It is a prediction of how the jet physics changes with the power of the central engine. And while the simple version of the sequence has been challenged by the discovery of objects that violate its expectations, high-luminosity BL-lac objects, for example, which should not exist according to the simplest version of the sequence, the broad physical interpretation has held up as a useful framework for understanding why Blazar populations look the way they do. It is at this point, with the Blazar taxonomy laid out, that the unified model of AGN becomes not just a classification tool, but a genuine physical statement about the structure of galaxies with active nuclei. The idea, developed over the 1980s and 1990s primarily by Celestino Barthel, Chris Urey, Paolo Padovani, and many others building on earlier work, is that the different classes of AGN, Seyfert galaxies, radio galaxies, quasars, and blazars, are all the same type of object viewed from different angles. The key ingredient is the obscuring torus and the orientation of the jet axis. If the AGN has a powerful jet and you observe it from a large angle, looking at it from the side, essentially, you see a radio galaxy. The jet appears as extended lobes of radio emission, but the inner accretion engine is seen through the obscuring torus and appears as a narrow-line radio galaxy, with only the narrow forbidden emission lines visible from the outer regions of the AGN. If you observe the same jet-powered AGN from a slightly smaller angle, not looking directly down the jet, but at maybe 20 to 40 degrees from the jet axis, you can see into the torus opening around the poles. You see the broad emission lines from the broadline region, and you observe what is classified as a quasar or radio-loud quasar. And if you observe this same system from an angle very close to the jet axis, within perhaps 10 degrees or fewer, the relativistic beaming of the jet dominates everything, and you observe a blazar. The model is elegant and has strong observational support. The numbers add up approximately correctly. The fraction of AGN classified as blazars relative to radio galaxies is broadly consistent with what you would expect if blazars are radio galaxies with their jets pointed toward the observer, when you account for the solid angle subtended by the beaming cone. The spectral properties of blazars match expectations for jet-dominated emission. The extended radio lobes that are clearly present in resolved radio galaxy images are absent in blazars not because they do not exist, but because the beaming amplifies the core jet emission so strongly that the lobes, which are not beamed, become subdominant. But the model is not perfect. There are complicating factors. The division between BL-lac objects and FSRQs does not map cleanly onto a simple orientation difference. There appear to be intrinsic differences in accretion rate and environment between the two classes. There are objects called changing look AGN that shift between spectral types on human timescales, suggesting that orientation alone cannot explain all the variability in AGN appearance. And there are borderline objects, including the prototype BL Lacertae itself, that have recently been found to exhibit behavior that crosses the boundaries between the established classes in ways that are genuinely not yet explained. A 2025 study by a Polish-German research team, published in Astronomy and Astrophysics, found that BL Lacertae itself was behaving in a way that escaped its own classification. During different observational periods, BL Lacertae showed X-ray signatures characteristic of high-energy blazars, then switched to signatures characteristic of low-energy blazars. And the switch happened on very short timescales in a manner that the researchers described as unprecedented and physically inexplicable within current frameworks. The prototype of the BL-lac class was violating its own category. The researchers called it a cosmic chameleon, and that label captures something important. The universe's objects do not always respect the tidy bins we build for them. Part 7. The flickering engine. One of the things that separates blazars from most other objects astronomers study, and one of the things that makes them both frustrating and deeply revealing, is how dramatically and rapidly they change. Most astrophysical sources are stable on human timescales. The sun will not vary detectably in luminosity over your lifetime. A distant quasar observed today and again in a year will look essentially the same. Even the most dramatic non-transient astrophysical phenomena, Supernovae, for example, evolve slowly enough that the full arc of their brightening and fading takes months. The universe, in most directions and at most wavelengths, is reassuringly stable from night to night and year to year. Blazars are not. A blazar can change its brightness by a factor of 2 in less than an hour. In some extreme cases, the doubling time for gamma-ray emission, the time it takes for the brightness at gamma-ray wavelengths to double, has been measured in minutes. There are documented cases of blazars varying by a factor of 10 or more in optical brightness over the course of days. There are blazars that astronomers have observed to go from a state of relative quiescence to intense high-energy flaring within hours, then settle back again, then flare again. The behavior described not as periodic, but as erratic, bursty, and complex, in a way that reflects the underlying turbulence and dynamics of the jet emission region. The Blazar PKS 2155-2304, a BL-LAC object located about 1.3 billion light-years from Earth, and one of the most intensively monitored Southern Hemisphere blazars, produced extraordinary TeV flares in July 2006 that remain among the most rapid high-energy variability events ever recorded. During the peak of this event, the TeV flux doubled on timescales of just a few minutes, far faster than any standard jet model with a single emission region could easily accommodate. The emitting region implied by this variability timescale, after correcting for the Doppler compression of timescales due to the jet's bulk motion, was about 2 orders of magnitude smaller than the size of the black hole shadow, the region of space immediately surrounding the event horizon. This is a fundamental challenge. How does a region so small produce such an intense outburst? And how is that region accelerating electrons to TeV energies so rapidly? Various models have been proposed. One class invokes a jet within a jet structure, in which the bulk of the jet's plasma moves at a moderate Lorentz factor, while small, compact subregions, perhaps formed by magnetic reconnection events or by instabilities in the jet's magnetic field, move at much higher Lorentz factors. These fast subregions, sometimes called blobs or plasmoids, produce the most rapid variability. Another class invokes the properties of the ergosphere itself, variations in the jet power at its launch point near the black hole, driven by oscillations in the accretion flow or the magnetic flux threading the horizon, could produce rapid variability in the jet emission at large scales that is then amplified by Doppler effects. A third class focuses on the role of stars or dense gas clouds that occasionally cross the path of the jet, providing compact targets for particle acceleration within the jet body that flare brightly and then dissipate. None of these models has been conclusively confirmed for any specific blazar, and it is entirely possible that different mechanisms dominate in different sources or during different phases of the same source's activity. The rapid variability problem remains one of the most actively debated issues in blazar physics, and it will likely require the next generation of very high-energy gamma-ray telescopes and rapid-cadence multi-wavelength monitoring campaigns to resolve. To understand why blazars flare and vary so rapidly, you need to understand something about the emission mechanisms that produce the radiation we observe. Blazar jets radiate primarily through 2 physical processes, and together, these processes produce the characteristic double-humped spectral energy distribution, the graph of how much energy the blazar emits at different frequencies. That is one of the defining observational features of these objects. The first process is synchrotron radiation. When a relativistic electron, an electron moving at close to the speed of light, spirals around a magnetic field line, it radiates. The frequency of the emitted radiation depends on the strength of the magnetic field and the energy of the electron. In blazar jets, where electrons can have energies far higher than anything achievable in Earth-based particle accelerators and magnetic fields are intense, this synchrotron process produces radiation that can span from radio waves all the way through optical, ultraviolet, and for the most energetically extreme jets, into the X-ray band. The lower energy synchrotron hump in the blazar spectral energy distribution is the signature of this process. The second process is inverse Compton scattering. Regular Compton scattering involves a high-energy photon transferring some of its energy to a low-energy electron. Inverse Compton scattering is the reverse. A high-energy electron collides with a low-energy photon and transfers energy to it, boosting the photon to much higher energies. In a Blazar jet, the abundant relativistic electrons have two main sources of photons to upscatter. They can upscatter the synchrotron photons they themselves produced, a process called synchrotron self-Compton, or SSC, or they can upscatter photons that come from outside the jet, from the accretion disk, from the broadline region, from the torus, a process called external Compton, or EC. In either case, the result is that photons that started at radio or optical frequencies get boosted to X-ray or gamma-ray energies. This is the origin of the high-energy hump in the Blazar spectral energy distribution, and it is why blazars are among the brightest sources of gamma rays in the extragalactic sky. The Fermi Gamma Ray Space Telescope, launched by NASA in June 2008 and still operating, has been a transformative instrument for blazar science. Its large-area telescope performs a continuous all-sky survey in gamma rays from about 20 MeV to more than 300 GeV, producing daily measurements of every significant gamma-ray source in the sky. Of the sources detected in the Fermi-Lat catalog, there are now more than 6,000 confirmed sources in the latest catalog releases. Blazars make up the vast majority. They are, by a wide margin, the dominant class of extragalactic gamma-ray emitters in the survey. Now, back to the variability. The reason blazars vary so rapidly comes down to the physics of emission region size and the light travel argument that has already appeared in this video. If a source of radiation is varying coherently, meaning the whole source brightens and dims together, then the source cannot be larger than the distance light can travel in one variability timescale. If a blazar doubles its gamma-ray brightness in 1 hour, then the emitting region producing that gamma-ray emission must be smaller than the distance light travels in 1 hour, which is approximately 1.08 billion kilometers. In astronomical units, that is about 7 astronomical units, less than the distance from the Sun to Jupiter. For a region within the jet of a galaxy a billion or more light-years away to vary this rapidly, the emitting region must be genuinely compact. Combined with the Lorentz factor corrections for the time compression caused by the near-light-speed motion of the jet material toward us, which can compress apparent variability timescales by factors of 10 to 30 relative to the intrinsic timescale in the jet's rest frame, this places the physical size of the most rapidly varying blazar emission regions at scales of a few light hours in the jet's rest frame. These are tiny emitting regions, compact knots or plasmoids within the broader jet structure, that are producing the most dramatic gamma-ray flares we observe. The physical origin of these compact, rapidly flaring emission regions is itself an active area of research with multiple competing models. The shock and jet model, the most historically dominant framework, proposes that shocks moving through the jet, analogous to sonic booms, but in a relativistic plasma rather than air, compress and heat the electron population in compact regions, dramatically increasing both the synchrotron and inverse Compton emission from those regions as the shock passes through. The magnetic reconnection model, which has gained considerable traction over the past decade, proposes that regions of oppositely oriented magnetic field within the jet, the complex helical field structure threading the jet, can create regions where the field topology is unstable, snap and reconnect, releasing enormous amounts of stored magnetic energy and rapidly accelerating the electron population. Particle-in-cell simulations, which model the behavior of individual plasma particles in electromagnetic fields and are only now reaching the computational maturity to be directly compared with observations, have shown that magnetic reconnection in relativistic jets can produce the kind of rapid, intense particle acceleration needed to explain minute-scale TeV flares. The jury is still out between models for any specific blazar flare, and the truth is likely that different flaring episodes in the same blazar reflect different physical mechanisms at different locations in the jet and different points in the jet's evolution. Blazars are not simple. They are complex, time-varying systems, and their variability is a record of processes operating simultaneously at different scales in the jet that we are only beginning to read clearly. What makes this variability scientifically valuable, beyond its intrinsic fascination, is that it is a diagnostic tool. The time scale of variability constrains the size of the emitting region. The spectrum of the flare constrains the energy distribution of the electron population. The correlation between variability at different wavelengths, whether the X-ray and gamma-ray flares happen simultaneously or with a lag, constrains the physical relationship between the electron population and the seed photon fields. The polarization of the optical and X-ray emission during flares constrains the geometry and coherence of the magnetic field in the emitting region. Every light curve, every spectral snapshot, every polarimetric measurement of a flaring blazar is a data point in a vast observational campaign aimed at understanding what is happening in a region a few light hours across, a billion or more light years away, in the most extreme particle acceleration environment in the known universe. Markarian 421, one of the nearest known blazars at a distance of about 400 million light-years, was the first blazar detected at TeV gamma-ray energies. The discovery was made in 1992 by the Whipple Observatory's Atmospheric Cherenkov telescope, and it was a landmark, the first confirmed detection of extragalactic gamma radiation at TeV energies. Markarian 421 has since been one of the most intensively monitored blazars in the sky, observed across radio, optical, X-ray, and gamma-ray wavelengths in dozens of multi-wavelength campaigns over more than 3 decades. Its behavior has confirmed and refined key aspects of the Blazar emission models. During its most active states, its X-ray flux can vary by a factor of 10 over the course of a day, and its TeV gamma-ray flux by even larger factors. Markarian 501, located at a comparable distance to Markarian 421 and also classified as a high-frequency peaked BL-LAC object, showed an extraordinary outburst in 1997 in which its TeV emission increased by nearly 2 orders of magnitude over its quiescent state. It briefly became one of the brightest objects in the TeV sky. The peak synchrotron frequency of Markarian 501 shifted to higher energies during this outburst, suggesting that the electron population in the jet was being accelerated to higher energies than usual, in a manner that is still not fully reproduced by standard theoretical models. In 2022, the Imaging X-ray Polarimetry Explorer, IXP, made direct measurements of the X-ray polarization of Markarian 501 during active states. Polarization measurements are particularly valuable because they constrain the geometry of the magnetic field in the emitting region. The IXP results showed that the X-ray polarization was higher than the optical polarization, which is consistent with a picture in which the X-ray emission comes from a more ordered, more compact region of the jet than the optical emission. The shocks that accelerate electrons to X-ray emitting energies appear to organize the local magnetic field more efficiently than the broader jet body does. These studies, across multiple blazars and multiple wavelength regimes, are assembling a picture of the jet emission zone that is more complicated and more interesting than early simple models suggested. The jet is not a single uniform structure. It is a complex, turbulent, time-varying column of plasma with shocks, reconnection sites, magnetic knots, and regions of accelerated particle populations at different scales, all contributing to the time-averaged and time-variable emission we observe. Resolving which physical process dominates in which source at which time requires exactly the kind of simultaneous, multi-wavelength, high-cadence monitoring that the current generation of telescopes, Fermi-LAT in gamma rays, Swift and NuSTAR in X-rays, the Very Large Telescope and various robotic optical telescopes in the optical band, the VELBA in the radio, is designed to provide. Every flare, every spectral shift, every minute-scale brightening in a blazar spectrum is a message from the jet. The message is written in the language of high-energy physics, and we are still learning to read it. Part 8. Messengers from the Edge. For most of the history of observational astronomy, the only messenger we had from the universe was light. In its many forms, radio waves, infrared, optical, ultraviolet, X-ray, gamma ray, electromagnetic radiation was the sole carrier of information we could collect, analyze, and use to map the universe. Everything we knew about stars, galaxies, quasars, and black holes came from photons that had traveled across cosmic distances and found their way to our instruments. That monopoly is over. Over the past 2 decades, and with particular intensity in the years since 2015, astronomy has become a multi-messenger discipline in a literal sense. Gravitational waves, detected for the first time by the LIGO collaboration in September 2015, gave us a completely new way to observe the mergers of compact objects, black holes, neutron stars, that are largely invisible to electromagnetic telescopes, and neutrinos, almost massless, electrically neutral, and interacting so rarely with ordinary matter that trillions pass through your body every second without disturbing a single atom, have provided a third messenger, one whose directionality and energy encode information about the most extreme particle acceleration environments in the universe. Blazars are at the center of the neutrino story, and the story begins with an observation made on September 22, 2017. On that date, the IceCube Neutrino Observatory, an instrument buried deep in the ice below the South Pole, consisting of 5,160 optical sensors strung along 86 vertical cables reaching depths of up to 2.5 kilometers in the Antarctic ice, detected a high-energy neutrino. The detection was labeled IceCube 170922A. The neutrino had an energy of approximately 290 tera-electron-volts, 290 trillion electron volts. For context, the protons accelerated in the Large Hadron Collider at CERN reach energies of about 6.5 tera-electron-volts at maximum. The neutrino detected by IceCube that September morning was carrying roughly 45 times the energy of the world's most powerful particle accelerator's beam, and it had arrived from outside the Milky Way, from somewhere in the direction of the constellation Orion. The IceCube team immediately circulated an alert, a notification to the broader astronomical community containing the direction and energy of the event, and telescopes around the world and in orbit began pointing in the indicated direction. What they found was a blazar. The blazar was identified as TXS 0506+056. It was a previously known gamma-ray source, but one that had been relatively little studied. When the multi-wavelength campaign kicked off in the days following the neutrino detection, TXS 0506+056 was found to be in a bright gamma-ray flaring state. The Fermi satellite confirmed it had been brightening by a factor of roughly 6 in gamma rays in the weeks leading up to the neutrino detection. The MAGIC telescope array in the Canary Islands detected it at very high-energy gamma rays, above 100 GeV on October 4th, the first detection of this source at those energies. The spatial coincidence between the neutrino direction and the position of TXS 0506+056, combined with the simultaneous gamma-ray flare, gave a chance coincidence probability of less than 1 in 1,000. The statistical significance was assessed at roughly 3 sigma. TXS 0506+056 is located at a redshift of approximately 0.3365, a distance of roughly 4 billion light-years. The neutrino detected by IceCube had therefore been traveling for 4 billion years from its point of origin to reach the Antarctic ice that morning in September 2017. To produce a neutrino of 290 tera-electron-volts, the source must have been accelerating particles, almost certainly protons, to energies at least this high. The standard mechanism by which high-energy neutrinos are produced is through the decay chain initiated when an extremely energetic proton collides with a photon and produces pions. The pions then decay into muons and muon neutrinos, with the muons subsequently decaying into electrons, electron neutrinos, and more muon neutrinos. This photomeson process, technically called pion photoproduction, is efficient when a beam of extremely energetic protons encounters a dense field of photons at the right energy range. In a blazar, the intense photon field from the accretion disk and the broadline region provides exactly this target for the protons in the jet. The detection of IceCube 17170922A from the direction of TXS 0506+056 was the first direct observational link between a high-energy astrophysical neutrino and a specific extragalactic source. It was, in a phrase used by many astronomers at the time, the birth of neutrino astronomy in a meaningful, source-resolved sense. The only previous confirmed sources of detectable neutrinos were the Sun, emitting low-energy neutrinos from its nuclear fusion processes, and the supernova 1987A in the Large Magellanic Cloud, which produced a burst of neutrinos that were detected by 3 independent instruments over a span of about 13 seconds on February 23, 1987. Everything since then in the neutrino sky had been a diffuse background, evidence that some astrophysical sources were producing high-energy neutrinos, but no clear assignment of that diffuse flux to specific sources. TXS 0506 plus 056 changed that. It was the third astrophysical source of detected neutrinos, and the first at high energies that was not inside or immediately adjacent to the Milky Way. But the story did not stop there. When the IceCube team went back and searched their archival data for historical neutrinos from the direction of TXS 0506 plus 056, they found something unexpected and intriguing. There was a significant excess of neutrino events, about 13 plus or minus 5 above background, coming from the direction of TXS 0506 plus 056 over a period from September 2014 through March 2015, roughly 2.5 years before the 2017 event. This archival neutrino flare had a significance of approximately 3.5 sigma. Interestingly, the 2014 to 2015 period did not correspond to a prominent gamma-ray flare in the Fermi data. The Blazar appeared relatively quiescent in gamma rays during that period, while apparently producing an excess of neutrinos. This raised a puzzle that has not been cleanly resolved. In models where neutrino production is directly linked to gamma-ray production through the same pion photoproduction process, which would mean that gamma-ray and neutrino production should be correlated, the apparent neutrino flare without accompanying gamma-ray activity is difficult to explain. Various theoretical frameworks have been proposed to account for this, including scenarios where the gamma-ray emission produced in the pion decay chains is reabsorbed within the source before it can escape, or where the neutrino production region is physically separate from the region producing the observed gamma-ray variability. None of these explanations has become universally accepted, and the 2014 to 2015 neutrino flare from TXS 0506 plus 056 remains an active puzzle. More recently, analysis of a large catalog of IceCube neutrino events and their spatial correlations with known blazars has provided additional evidence that the blazar population contributes significantly to the observed diffuse astrophysical neutrino flux. A study led by Sarah Buson at the University of Würzburg, published using data from the IceCube collaboration, found that at least 10 of the 19 brightest neutrino hotspots in the southern sky correspond to known blazars. The most powerful blazars in this context, called pevotron blazars, because they can accelerate particles to peta-electron-volt energies, show the strongest associations. The statistical evidence, while stopping short of definitive detection for individual sources beyond TXS 0506 plus 056, points convincingly to blazars as a significant class of extragalactic neutrino producers, and therefore, as one of the primary sources of the highest energy cosmic rays in the universe. The connection to cosmic rays deserves its own emphasis. Ultra-high energy cosmic rays, protons and atomic nuclei arriving at Earth with energies that can exceed 10 to the power of 20 electron volts, 100 billion times the energy of the neutrino detected from TXS 0506 plus 056, have been one of the great mysteries of high-energy astrophysics for decades. These particles carry so much energy that when they hit the upper atmosphere, they initiate cascades of secondary particles detectable by ground-level arrays of particle detectors spanning areas of thousands of square kilometers. Their origin has been debated for decades. Because they are charged particles, their trajectories are bent by the magnetic fields of the intergalactic medium as they travel from their sources to Earth, making it difficult to trace them back to specific objects. Neutrinos, being electrically neutral, do not have this problem. They travel in straight lines from their sources to our detectors, which is why the detection of neutrinos from the direction of TXS 0506 plus 056 was so significant. The emerging consensus, still being refined with ongoing observations, is that blazars, or at least the subset of blazars with the most powerful jets and the highest accretion luminosities, are among the primary sources of ultra-high energy cosmic rays in the universe. The jets of these objects are particle accelerators on a cosmic scale. They can accelerate protons to energies that dwarf anything achievable on Earth. And when those protons interact with the photon fields within the jet, they produce the neutrinos we are now detecting. In October 2025, a study published in Nature identified the Blazar PKS 1717 plus 177, located roughly 600 million light-years away, as a potential source of an ultra-high energy cosmic ray event called Amaterasu, a 2021 detection of a cosmic ray with an energy exceeding 2 × 10 to the power of 20 electron volts, which is one of the most energetic cosmic ray events ever recorded. Modeling of the blazar's jet environment showed that it was capable of accelerating protons to the required energies, and that the most energetic protons escaping the jet could travel across intergalactic space, deflected by the intervening magnetic fields, and arrive at Earth in the approximate direction observed. We are entering a phase of astronomy where individual blazars are being identified as the specific engines behind the most energetic particles and messengers ever measured. The objects that Kuno Hofmeister catalogued as oddly behaving variable stars in 1929, and which John Schmidt began to unravel in 1968, and which a generation of radio astronomers gradually recognized as a population of jet-pointed AGN, are now being revealed as the most powerful particle accelerators in the observable universe. They are producing particles at energies that make the word acceleration feel inadequate, and they are sending us neutrinos that, for the first time, allow us to point back at their sources with confidence. Part 9. The Cosmic Accelerator Problem. When you receive a postcard, it tells you 2 things: where it came from, and something about what is happening there. Before we get into the neutrino story in depth, it is worth pausing to appreciate the sheer scale of what the question of cosmic ray origins represents. Cosmic rays are not exotic or rare. They are impacting Earth continuously. Every second, roughly 1 cosmic ray particle passes through each square centimeter of the upper atmosphere somewhere on our planet. At lower energies, the flux is high enough that several cosmic ray particles pass through your body every minute without you noticing, carrying far less energy than the natural radioactivity already present in your cells. The lower energy cosmic rays, the majority, in terms of numbers, have been understood for decades. They are accelerated primarily by supernova shock waves within our galaxy, the expanding shells of material flung outward when massive stars explode at the end of their lives. These shocks are efficient accelerators of charged particles, producing a power law spectrum of particle energies that matches what we measure in the cosmic ray spectrum up to around 1,000 teraelectronvolts, the so-called knee in the spectrum where the slope steepens. Above the knee, things become murkier. The highest energy cosmic rays, those with energies of 100,000 teraelectronvolts and above, the ultra-high energy cosmic ray region, cannot be produced by supernova shocks within our galaxy. The physics simply does not allow it. To accelerate a proton to these energies by the shock acceleration mechanism requires either a shock region large enough to contain the particle's gyro radius in the ambient magnetic field, or a magnetic field strength and shock speed combination that exceeds what supernova remnants can provide. The sources of the highest energy cosmic rays must be extragalactic, and they must involve processes operating at a scale of energy density and power that has no equivalent in ordinary stellar physics. This is where blazars enter the cosmic ray story. The relativistic jets of blazars satisfy the basic energetic requirements that the highest energy cosmic rays demand. The jet extends over large enough scales. The magnetic fields within it, though uncertain, appear sufficient. The bulk energy of the plasma flow, carrying protons accelerated to extreme energies by the shock and reconnection processes operating throughout the jet, is more than adequate. and the photon density within the jet, from the synchrotron photons produced by the jet's own electrons, from the accretion disk photons illuminating the jet from below, from the broadline region photons surrounding the jet at small distances from the black hole, provides exactly the target material needed for the pion photoproduction that generates the neutrinos we detect. The challenge has been connecting these theoretical expectations to specific observational detections. Cosmic rays cannot be traced back to their sources because they are deflected by the intergalactic magnetic field during their journey to Earth. The deflection angle depends on the particle's charge, its energy, and the integrated magnetic field along its path. For the very highest energy cosmic rays, those above about 60 times 10 to the power of 18 electron volts, where the GZK cutoff begins to suppress the flux, the deflection angles are smaller, potentially small enough that the arrival direction of the cosmic ray roughly corresponds to the direction of its source. This is why the Pierre Auger Observatory in Argentina, which detects ultra-high energy cosmic rays through the enormous air showers they generate in the atmosphere, has looked for correlations between the arrival directions of the highest energy events and the positions of known AGN and Blazars in catalogs. The statistical correlations found by Auger are suggestive but not yet definitive, partly because of the uncertainties in the intergalactic magnetic field deflections, and partly because of the limited statistics at the very highest energies where the flux is small. The neutrino is the cleanest tracer of the hadronic acceleration process, and the ice cube detections have provided the most compelling evidence to date. It is worth understanding precisely why this is. In the pion photoproduction process, a high-energy proton collides with a photon and produces a pion, a particle made of a quark-antiquark pair, along with other products. Charged pions decay quickly into muons and muon neutrinos, and the muons subsequently decay into electrons and additional neutrinos. Neutral pions decay into 2 gamma-ray photons, so the same process that produces neutrinos also produces gamma rays. If you detect a high-energy gamma ray and a high-energy neutrino simultaneously from the same source, you have a strong argument that both were produced by the hadronic process, that protons were being accelerated there to extreme energies and interacting with the ambient photon field. The TXS 0506 plus 056 event in September 2017 was precisely this kind of coincidence. A 290 tera-electron-volt neutrino arrived simultaneously with an enhanced gamma-ray state from the Blazar. The same physical process, proton acceleration and pion photoproduction, likely produced both messengers. The Blazar had been functioning as a hadronic accelerator during that period, and we caught it in the act. The story of multi-messenger astronomy and blazars is still being written. Future neutrino observatories, the IceCube upgrade, the proposed IceCube Gen 2 expansion that would increase the instrumented volume by roughly an order of magnitude, the Baikal GVD telescope operating in Lake Baikal in Russia, the KM3NET telescope currently being built under the Mediterranean Sea, will provide dramatically improved sensitivity for detecting high-energy neutrinos and correlating them with electromagnetic sources. The combination of these future neutrino instruments with the expanded gamma-ray capabilities of the Cherenkov telescope array and with next-generation radio and X-ray survey telescopes will provide a multi-messenger view of the Blazar sky that will, within the next decade or two, settle many of the questions that are currently open about the hadronic content of Blazar jets and the contribution of blazars to the cosmic ray flux. We are entering a phase of astronomy where individual blazars are being identified as the specific engines behind the most energetic particles and messengers ever measured. The objects that Kuno Hofmeister catalogued as oddly behaving variable stars in 1929, and which John Schmidt began to unravel in 1968, and which a generation of radio astronomers gradually recognized as a population of jet-pointed AGN, are now being revealed as the most powerful particle accelerators in the observable universe. They are producing particles at energies that make the word acceleration feel inadequate, and they are sending us neutrinos that, for the first time, allow us to point back at their sources with confidence. Photons are the postcards of the universe, and for a very long time, they were the only kind we knew how to read. But photons have limitations as messengers. Gamma rays at very high energies can be absorbed by the extragalactic background light, the diffuse sea of infrared and optical photons produced by all the galaxies in the universe over cosmic time. And this absorption means that the highest energy gamma rays cannot reach us from sources beyond a certain distance. Charged particles like protons and cosmic ray nuclei are deflected by magnetic fields and lose their directional information. What we needed was a messenger that could travel from extragalactic distances, carry directional information precisely, and be produced specifically by the kinds of extreme particle acceleration processes operating in the most energetic astrophysical sources. Neutrinos fit that description almost perfectly. The IceCube Neutrino Observatory was built precisely to exploit this. Located at the geographic South Pole, it uses the exceptionally clear Antarctic ice as its detector medium. When a high-energy neutrino, one of the rare ones that actually interacts with the ice rather than passing straight through, collides with a nucleus in the ice, it produces a secondary charged particle that travels faster than the speed of light in ice. Though not in vacuum, light travels more slowly in ice than in vacuum, so this does not violate special relativity. This faster-than-light in the medium travel produces a cone of Cherenkov radiation, a bluish glow analogous to the sonic boom of a supersonic aircraft, but in light rather than sound. The 5,160 optical sensors detect this Cherenkov glow and reconstruct the direction, energy, and time of the incoming neutrino. The relationship between blazars and the observed diffuse high-energy neutrino flux detected by IceCube over more than a decade of operation is one of the central open questions in high-energy astrophysics. The total flux of high-energy astrophysical neutrinos measured by IceCube, summed over all directions and all energies above about 10 tera-electron-volts, can be explained if blazars contribute somewhere between tens of percent and all of it, with the exact fraction depending on assumptions about the proton-to-electron ratio in blazar jets, which is poorly constrained, the density of the photon fields that serve as targets for pion production, and the fraction of blazar jet power that goes into accelerating protons to the relevant energies. That last question, the ratio of hadronic to leptonic power in blazar jets, is perhaps the most significant unresolved issue in blazar physics right now. Leptonic jets are dominated by electrons and positrons. They radiate primarily through synchrotron and inverse Compton processes, and they produce gamma rays, but very few neutrinos. Hadronic jets contain a significant fraction of protons accelerated to high energies. They produce neutrinos through pion photoproduction, but the same pion decay chains also produce secondary electrons and gamma rays that can contribute to the observed emission. The problem is that, from the electromagnetic spectrum alone, it is often very difficult to distinguish a primarily leptonic model from a primarily hadronic one. Both can be tuned to fit the observed spectral energy distribution. The neutrino is the unambiguous diagnostic. Only hadronic models predict them in detectable quantities. But detecting neutrinos from individual blazars requires both a bright, nearby source and a long period of observation. And IceCube's sensitivity, though extraordinary, is still limited for individual source detections. The multi-messenger approach, combining electromagnetic data from radio to gamma ray, neutrino data, and potentially future cosmic ray arrival direction data from next-generation observatories, is the path forward. The Cherenkov Telescope Array, an array of imaging atmospheric Cherenkov telescopes currently under construction at sites in Chile and the Canary Islands, will provide gamma-ray sensitivity roughly 10 times better than current instruments across a broader energy range, and its ability to detect time-correlated gamma-ray and neutrino events from individual blazars is expected to significantly advance our understanding of whether specific blazars are producing the observed neutrino flux, and through what mechanisms. The deeper implication of the blazar cosmic ray connection is that these objects are not just dramatic spectacles in the high-energy sky. They are contributing to the physical environment of the universe in ways that extend far beyond the galaxies they inhabit. The ultra-high-energy protons escaping from blazar jets become part of the diffuse extragalactic cosmic ray flux that permeates the universe. when they interact with the cosmic microwave background over their journey to Earth, a process that limits the distance from which we can detect the very highest energy cosmic rays, known as the GZK cutoff, after Greisen, Zatsepin, and Kuzmin, who predicted it independently in 1966. They produce secondary gamma rays and neutrinos that add to the diffuse backgrounds we measure. Blazars are therefore not just local phenomena. They are contributing to the energy budget and particle content of the universe at large. There is also a connection between blazars and the extragalactic magnetic field, the weak, pervasive magnetic field that permeates the space between galaxies, that is subtle but real. Charged particles escaping from blazar jets contribute to this field. The jets themselves, extending for millions of light years beyond the host galaxy, carry magnetic energy into the intergalactic medium, and the very high-energy gamma rays from blazars that are absorbed by the extragalactic background light produce electron-positron pairs, which subsequently interact with the cosmic microwave background and generate secondary gamma rays that we observe at lower energies as a diffuse background. The entire electromagnetic environment of intergalactic space is in part shaped by blazar activity over cosmic time. These are not second-order effects. Galaxy formation simulations increasingly include AGN feedback, the energy injected by supermassive black holes into their environments, as a critical ingredient for reproducing the observed galaxy distribution. The jets of radio-loud AGN, of which blazars are the extreme aligned subset, heat and stir the gas in galaxy clusters, suppressing the cooling that would otherwise lead to runaway star formation in the most massive galaxies. The energy balance of the universe, on scales from kiloparsecs to megaparsecs, is influenced by the same engines that produce the neutrinos arriving at ice cube sensors deep in the Antarctic ice. The blazar, observed as a brilliant flickering point of light in the direction of the Lizard or Orion or any of the other constellations they happen to inhabit in our sky, is embedded in a web of physical consequences that extends to the largest scales of observable structure. Part 10. What we do not know. It would be intellectually dishonest, after spending so long building an edifice of understanding around blazars, to end without an equally thorough accounting of what remains unknown. Science is not a collection of answers. It is an ongoing argument with the universe, and the universe wins more often than the textbooks suggest. The most fundamental unsolved problem in blazar physics is the one we have circled repeatedly throughout this video without fully resolving: the jet formation mechanism. We have the Blanford's-Najek process as the leading theoretical framework for how rotational energy from a spinning black hole can be converted into a relativistic jet through electromagnetic effects in the ergosphere and magnetosphere. We have general relativistic magnetohydrodynamic simulations that show jet-like structures launching from the vicinity of black holes under the right conditions. We have the Event Horizon Telescope's image of the M87 system, which shows a jet whose base lies within a few Schwarzschild radii of the central black hole, and whose structure is broadly consistent with the Blanford's-Najek expectation. But we do not yet have a predictive theory that, given the mass of the black hole, its spin, the accretion rate, and the magnetic field configuration, can calculate the jet power and Lorentz factor from first principles with the accuracy needed to match observations. The parameters that control the actual efficiency of the Blanford's-Najek process in real accreting systems, how much magnetic flux actually accumulates near the horizon, how the disk corona jet system exchanges angular momentum, what determines the Lorentz factor of the bulk flow, are not cleanly calculated from first principles in current models. They are constrained by observations and matched by simulations. But the physical intuition for why blazars have the Lorentz factors they have, why some jets are faster than others, why the Lorentz factor distribution spans the range it does across the blazar population, remains incomplete. The question of what fraction of the blazar jet power is hadronic, carried by protons, versus leptonic, carried by electrons and positrons, is tightly bound to the neutrino question and remains unresolved. If blazar jets are predominantly leptonic, they contribute negligibly to the observed cosmic ray and neutrino fluxes. If they are significantly hadronic, they may be among the dominant sources. The observational evidence from IceCube points toward a hadronic contribution, but the quantitative level is uncertain, and different blazars may have different proton fractions depending on their luminosity, accretion state, and environment. There is also the question of jet composition at the particle level, whether the positrons in the jet are produced locally by pair creation processes driven by the jet's own gamma-ray emission, or whether they were accelerated from a seed population of electron-proton plasma from the accretion disk. This distinction matters for the total mass and kinetic energy of the jet, and for understanding how the jet propagates through the host galaxy and beyond. Current observations of the circular polarization of Blazar radio emission, a signature that in principle distinguishes electron-proton from electron-positron plasmas, have given conflicting results in different sources, and there is no consensus on the typical composition. The classification problem we encountered in the case of Blazar itself, the cosmic chameleon that switches between high-energy and low-energy spectral behavior in a way that current models cannot explain, is symptomatic of a broader issue. The Blazar sequence, the organized progression from powerful FSRQs to low-peaked BL-lax to high-peaked BL-lax, is a useful organizing framework, but individual sources deviate from it in ways that are not accounted for. Changing-look blazars, objects that shift their spectral properties between blazar classes on observable timescales, suggest that the accretion state and jet properties can change rapidly enough to move an object between categories, in a manner that calls into question how stable and fundamental those categories really are. There are also deeper questions about the relationship between blazars and the galaxies they inhabit. The correlation between black hole mass and the mass of the stellar bulge of the host galaxy, the so-called M-sigma relation, is one of the most discussed empirical regularities in extragalactic astronomy, and it suggests that the growth of black holes and the growth of their host galaxies are tightly coupled over cosmic time. Blazars represent episodes of extreme black hole activity. How those episodes relate to the star formation history and structural evolution of the host galaxy, whether the jet is suppressing or triggering star formation, whether the feedback from the jet is heating the intracluster medium on megaparsec scales in ways that affect the broader group or cluster environment, are active research areas with observations that do not yet fully constrain the models. And there are questions that are not specific to blazars, but in which blazars play a key role. The nature of the extragalactic background light, which is mapped partly through the absorption of blazar gamma rays at different energies, the intergalactic magnetic field, which is constrained partly through the cascade gamma ray emission produced by absorbed blazar photons, the composition and power spectrum of the cosmic ray background, the total contribution of AGN feedback to the heat budget of the universe. None of these are trivial technical details waiting for a new data set to resolve them. They are genuine open questions at the frontier of our understanding of how the universe works at its most energetic scales. What makes blazars uniquely valuable in this landscape is that they are, in a sense, maximum experiments. When you want to understand jet physics, you study blazars because the jet is pointing at you and you are seeing it at maximum amplification. When you want to understand extreme particle acceleration, you study blazars because they produce the highest energy neutrinos from identified extragalactic sources. When you want to understand the most extreme variability achievable in persistent astrophysical sources, you study blazars because they can change by factors of 10 or more on timescales of hours. They are the universe running its most extreme processes with the volume turned all the way up in our direction. And the irony of all of this is that this extraordinary window into extreme physics is entirely a product of geometry. The blazar is not a special kind of object. It is not doing anything unique. It is the same engine as 1,000 radio galaxies, whose jets are pointed in other directions. The same engine as 1,000 quasars, whose jets we see at intermediate angles. The same engine that sits quietly in the centers of elliptical galaxies across the universe. The accident of AIM, the random cosmic alignment that positioned one of those jets so that it is pointed directly at the Milky Way and at the instruments we have built to observe it, is the whole story. There is no designed purpose here, no intentional signal being sent. It is geometry, pure and indifferent, that has placed us in the beam. But we are in the beam. And the physics at the end of that beam, the black hole spin, the ergosphere and the magnetic fields threading it, the relativistic plasma fired outward at speeds that make light itself only marginally faster, the Doppler boosting that amplifies everything, the synchrotron radiation and inverse Compton emission painting the full electromagnetic spectrum, the protons accelerating to energies that make Earth's most powerful machines look like toys, the neutrinos arriving at Antarctic ice after billion-year journeys from the jet's production region. All of that physics is real, and it is happening right now, in multiple directions across the sky, in sources that are changing as we watch. A blazar is not a distant curiosity. It is not merely an extreme object catalogued for its record-breaking properties. It is a window, or more precisely a barrel, a direct line of sight into the most energetic, sustained physical processes in the observable universe, processes that are shaping the intergalactic environment, producing the highest energy particles we have ever measured, and challenging the limits of our theoretical understanding at every frequency we measure them. The object Kuno-Hofmeister catalogued as a variable star in the Lizard constellation in 1929, and which turned out to be a supermassive black hole 900 million light-years away firing plasma at relativistic speeds in our direction, is still out there. It is still varying. It is still firing. It is, right now, as you watch this, doing exactly what it has been doing for billions of years, converting the spin of a black hole into radiation and particles, aimed at the particular direction in space that happens to be our address in the universe. We built the instruments that let us see it clearly enough to understand what we were looking at. That took nearly a century from the first misidentification in 1929 to the neutrino detection in 2017. It took radio telescopes, optical spectrographs, X-ray satellites in orbit, gamma-ray observatories, high-resolution, very long baseline interferometric arrays stretching across continents, a cubic kilometer of Antarctic ice, wired with thousands of optical sensors, and a global network of astronomers sharing data in real time. The Blazar did not announce itself. We had to build the eyes to see it for what it was. That effort, accumulating over decades, across institutions and countries and generations of researchers, is itself a kind of extraordinary thing. The universe presented us with an object that looked like an ordinary variable star. We kept looking, kept measuring, kept questioning, and eventually we understood that we were looking straight down the barrel of the most powerful sustained particle accelerator in the known universe, a billion light-years away. There is also something worth noting about our perspective as observers. We are, by any reasonable measure, in the beam of multiple blazars by pure accident. No aspect of our position in the Milky Way was selected for proximity to a blazar jet. The orientation of these jets relative to our line of sight is determined by the geometry of the host galaxies and the angular momentum of their central black holes, neither of which has any relationship to the position of the solar system within its own galaxy. We happen to be here. The beams happen to be pointed this way. The combination produced, for any intelligent civilization that evolved within this particular address in space, a sky containing objects of extraordinary explanatory richness, objects that force you to confront the physics of spinning black holes, relativistic plasma, and extreme particle acceleration just to understand why a point of light in a photograph is behaving the way it is. The universe did not arrange this for our benefit, but it did arrange it in a way that rewards curiosity with extraordinary depth. Every blazar in the sky is a door, and behind it is the same story. A black hole, a disk, a magnetic field, a jet, and a beam pointed, by cosmic accident, in our direction. Each one a different version of the same fundamental physics. Each one telling us something slightly different about what it takes, in real astrophysical conditions, to convert gravity and rotation into radiation at the most extreme scales the universe permits. That is what science does. It turns apparent simplicity into revealed depth. It turns a point of light into a black hole. It turns a mystery into a mechanism, and then it finds the next mystery hiding inside the mechanism. The universe keeps its most extreme processes running quietly and continuously. Most of the time, in most directions, there is nothing dramatic to see, but every now and then, the beam is pointing at you. And when it is, you get to watch something that has no equivalent anywhere in ordinary experience. Something that requires the full apparatus of general relativity, special relativity, quantum field theory, and plasma physics just to describe, and which still, in its finest details, resists complete understanding. That is the Blazar. That is what it really is. Not a star, not a simple radio source, not merely a bright dot in a catalog of bright dots. A rotating black hole using the warped geometry of its own spacetime to extract its spin energy through magnetic fields and fire it toward you, from a distance so large that the light you see left its source before the first animals with complex eyes evolved on Earth. And it has been doing this, continuously, patiently, without pause, without slowing, for longer than the Earth has existed. The universe does not hurry, but when it decides to be dramatic, it does not hold back. If this video helped you think about blazars, or the universe, or the way extreme physics hides in plain sight in an apparently quiet sky, hit like and subscribe, and leave a comment somewhere in here. Every comment is read, and these topics only go deeper from here. The next time you look at the night sky and see a faint point of light, consider the possibility, small but real, that what you are looking at is not a star at all. That it is a black hole billions of light years away, pointed at you. That the ancient light arriving at your eye right now left its source before complex animal life existed on this planet, fired outward by an engine that extracts energy directly from the geometry of space-time itself, and that it has crossed the void between galaxies only to end its journey in the retinas of a creature curious enough to ask what it is. That curiosity and the extraordinary universe it has revealed to us is the whole point. The sky rewards it, the physics rewards it, and every blazar out there, every spinning black hole with its beam aimed somewhere in the universe, is waiting to reward whoever happens to be standing in its path and paying attention. What is humbling, when you step back from all the technical detail we have covered tonight, is how recently we knew almost none of this. The 1920s astronomer who catalogued B.L. Lacerté had no concept of black holes. They were still theoretical curiosities not yet taken seriously by mainstream astronomy. The concept of a jet, of relativistic beaming, of gamma-ray emission from extragalactic sources, of neutrino astronomy, none of it existed as a practical observational reality. The entire edifice of understanding we have built around blazars is less than a century old, and much of it is less than 50 years old, and the neutrino connection is less than a decade old. We are at a genuinely early stage. The Cherenkov telescope array, the next generation of IceCube, future X-ray polarimetry missions, the Event Horizon Telescope's ongoing improvements in angular resolution, these instruments will, in the coming decades, reveal structure and behavior in blazar jets that we currently cannot even clearly formulate as hypotheses. The questions we will be asking in 2050 about blazars have not all been written yet, because some of them require observations we have not yet made and theoretical results we have not yet derived. The subject is alive and open and growing, and that, in the end, is the best thing you can say about any area of science. Sleep well,